Sorry, I'm getting a lot of interruptions today. Let's see if we can get through some more. So, next up is going to be the ConRod. And again, we're going to have a number of forces that are acting on it. And I'm going to draw them all in their positive direction. So we have still our x and y axes. We will have forces acting on the ConRod down at the connection to the piston. F3 to x, F3 to y. Up at the connection to the crank, F1 to x, F1 to y. We were given a center of gravity for the ConRod at its center, so we will have inertial forces acting on it as well, negative m2 a g2x, negative m2 a g2y, and a rotational inertia force, negative I g2 alpha g2, or alpha 2. So, this is fairly complex. There are a lot of equations that go into the ConRod, and it is definitely the key to the entire problem. So we're going to have to do some preliminary work to figure out what we can about it. If you recall from the discussion on the acceleration, we know that the acceleration at the center of gravity, a g2, is equal to, 319,507 millimeters per second squared, and it is an angle of 206 degrees. The ConRod itself is also at an angle. Going back to the original sketch, we can figure out what that angle is. So, to do that, we recognize that this is a right triangle whose height on this leg is defined by the right triangle formed by the crank. So, if I calculate this, height of that leg of the triangle will be the sine of 45 degrees times the length of OB. It tells me that this length is 28.3 millimeters. Therefore, I can get this angle by taking the inverse sine of 28.3 divided by the hypotenuse of this triangle, which is 100 millimeters. So 28.3 divided by 100, and to take the inverse sine, this angle is 16.4 degrees. So I'll write that in here so I have everything together. Now at this point I can start to do my sum of the forces, but I need to realize that this acceleration is going to have to be decomposed into an x component to get the inertia of the crank in the x-axis, and a y component to get the inertia of the crank in the y-axis. So let's first write our overall force balance equations. I know that I will have, let's see, let's start up here. These are going to get long. F12x plus F32x plus negative m2 ag2x is equal to 0. So that's my force balance in the x-axis. I will also have a force balance in the y-axis. Do this one perhaps over here. F12y plus F32y plus negative m2 ag2y is equal to 0. So far, so good. These two are fairly straightforward, and as you recall, we have a value for F23x calculated from the piston. Therefore, we know that F32x is equal and opposite. So we have a value here. We can also calculate some values for ag2x and y, which would allow us then to get inertial forces in both the x and y. So it's fairly straightforward to plug and chug and get a final value for F12x. However, we still have nothing for the y-axis. Let's go through the x portion, and then I will start a second video to delve into the y portion, because that gets a little crazy. First off, for ag2, this is an angle of 206 degrees. So if I draw my coordinate system, x and y, this vector is going down like this at an angle of 206 degrees. So the y portion will be negative, down like this, and it can be determined by calculating the length of this y vector based on the overall vector and the angle. So from my standpoint, I kind of look at it as a right triangle that does this. This included angle in the right triangle is 180 degrees less than 206. So that tells me that I have a 26-degree angle here. So basic sine relationship, this leg divided by this leg is equal to the sine of 26. Therefore, my AG to y is equal to, this is negative, remember, negative AG2 times the sine of 26 degrees. So, if I calculate that, I have 318,507, and I will go ahead and apply a negative to it right now. I will multiply that by the sine of 26, and I end up with negative 140,063 millimeters per second squared. That's AG2y. AG2x is just as straightforward to get. Oops. It's this leg of the triangle, and it is also in the negative direction, so it will be negative AG2 times the cosine of 26 degrees. So 319,507 cosine, and I get negative 287,171 millimeters per second squared. Now, if you recall, from the second problem, we have a mass for the ConRod of 0.2 kilograms. So that means that we can go ahead and calculate M2AG2x and M2AG2y. M2AG2x is equal to 287,171 times 0.2, and we'll divide it by 1,000, and we'll come up with negative 57.4 newtons. Obviously kind of goofy, you get a mass times acceleration, so the acceleration is negative. M2AG2y, in the same fashion, 140,063.2 times divided by 1,000 is negative 28 newtons. So now we can plug things in, and we'll do that maybe at the start of the next video, because this file's starting to get a little bit on the long side.